The Constitution of India. Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. Happy Onam to you and your family. I know today is already Avittam, and last 10 days you all would have got a great time with your parents, grandparents, family members at home. Yesterday being Thiruvonam, you would have all celebrated in a very different manner, and I hope you would have also participated in the school competition of sending your family pic with a different message, and let us eagerly wait for the results that is going to come on the following week. And I hope you all are doing good, but I know still many of you are longing to get back to the school at the earliest, right? So let us hope for the best. Let us pray Almighty again, because as of now nothing else is running in our mind except being in the school campus, which is going to be giving us more energy than anywhere else, right? So let us again pray God so that we all meet together here again and spend the rest of the days with great memories. Okay? And children, to begin today's class, last class I had sent a video and at the end of the session which was relating Kohlrausch law and conductivity of strong and weak electrolytes. If you can just recollect what was in the last class, because I haven't explained about the video, but I told you, you just see the video and we will be discussing about that in the next class. I hope many of you would have got some idea about conductivity or molar conductivity in strong and weak electrolytes. First of all, what are electrolytes? We know electrolytes can be acids, it can be bases, or it can be any salt which are carrying ions, that is charges, to conduct the electricity in the liquid or in the substance. Now we also learned that pure water do not conduct electricity, but when I am going to dip or when I am going to add some ionic substance into it, when I am going to add some electrolyte into it, an acid or a base or a salt, definitely ions get dissociated and it will produce electricity, or it will pass the electricity around the substance. So this is what we have been learning. Now how can I say that this is a strong electrolyte or this is a weak electrolyte? Now in 11th standard we have also learnt about dissociation constant. If you can remember, children, dissociation constant with Ka, that is for acid, Kb for base. Yes, Suvenya, can you just recollect? Yes, you are right. So those are the dissociation, power of dissociation or extent of dissociation. When I am going to put my sodium chloride, that is salt, in water, immediately dissociate into Na plus ions and Cl minus ion. That is the power of dissociation. But strong electrolytes can dissociate completely into cations and anions, but weak electrolytes only to a particular extent. They may not dissociate completely. So that dissociation will be resulting in the conductivity of the electrolyte. But we also learned that a normal conductivity, that is kappa, will be increasing or decreasing with concentration, but that is not the case with molar conductivity. It is actually inversely proportional. When my concentration increases, molar conductivity decreases, or when my concentration decreases, molar conductivity increases. This is what we learnt in the previous class. But today we will just see what are the formulas that we went through. We learnt about conductance, which is equal to kappa into A by L, that is on conditions when A is equal to 1 meter square and L is equal to unit length of 1 meter, then we know conductance will be equal to conductivity, which means whenever there is an increase in conductivity, the conductance of the substance also increases. That is directly proportional. And when we were coming into molar conductivity of solutions or for electrolytes, we learnt it is kappa into A by L. You children, I think you can also recollect now the use of conductivity cell. Between the two platinized electrodes, distance between the electrodes is L and the total volume is the area of cross section. So here in place of A, we also substituted V, which is the volume of the whole conductivity cell. So molar conductivity will be kappa into V. But what is important with respect to molar conductivity? When there is an increase in concentration. When there is an increase in concentration, what happens? The volume decreases, the area decreases, therefore the molar conductivity also decreases. And when there is a decrease in the concentration, the volume, that is what do you mean by decrease in concentration? Solution becomes dilute. When solution becomes dilute, the volume will be more. Whenever there is an increase in volume, the molar conductivity also increases because this is directly proportional. So this is what we learnt. Also we learned that molar conductivity is equal to kappa by C, where C is inversely proportional to lambda m, that is molar conductivity. In your textbook, instead of lambda, they would have also been given as Em, that is molar conductivity, or E naught m, which is limiting molar conductivity. So it is okay, both means the same. At the end of the session, we learnt one important term, which is limiting molar conductivity. The word limiting only suggests that when the concentration becomes absolutely zero. Zero means what? Perfectly diluted. The volume is so large. Whenever there is an increase in volume, it becomes so dilute that it reaches a particular value, which we call it as limiting molar conductivity. Now, we are going to discuss in this class what happens to the limiting conductivity or molar conductivity for strong and weak electrolytes. So, when I say a strong electrolytes, let us take an example of KCl. What actually happens with molar conductivity? It increases with dilution. That is, whenever the concentration is less, the molar conductivity becomes more. So, I can also write that molar conductivity will be equal to molar conductivity at infinite dilution minus AC power half. This is the equation which you should learn by heart. Okay. So, molar conductivity is equal to molar conductivity at infinite dilution, that is, or I can say limiting molar conductivity minus AC power half. But what happens here? When I say limiting molar conductivity, the volume is so high, it becomes so huge that the concentration is zero, it becomes less. Dilution is so much that the C becomes zero, that is for concentration. But what about my A? A depends on the nature of the electrolyte, which means either it is a strong electrolyte or it is a weak electrolyte. That is, whenever I say electrolyte, what plays an important role in electrolyte? It is nothing but the charge of ions. It can be cations, it can be anions, or we also learned that the number of ions per unit volume. So, whenever I say A, it depends on the nature of electrolyte, whether it is my strong electrolytes or it is a weak electrolyte. So, when I am going to draw a graph, when I draw a graph with molar conductivity and concentration power half, I get a slope like this, where the slope is my AC half and my intercept will be my limiting molar conductivity. In maths, you have learnt about intercept and slopes. You will not be asked to draw a graph. Instead, you can be given a graph and ask you to write about the strong electrolytes. But what is the original situation, children? What is exactly happening? So, whenever we take a mixture of electrolytes, now these are my strong electrolytes. Let us take sodium chloride, magnesium sulfate, calcium chloride. In each of these situations, if you see, what is this 1 1, 2 2, 2 1? These are my charge of the ions, because I told you here the value of A depends on the charge of the ion. What is the charge of sodium? It is Na plus 1. It loses 1 electron to become sodium. So here it is 1. What is this 1 here? This is Cl minus. That is minus 1. Chlorine gains 1 electron, right? So it becomes 1. So here again it is 2 2, Mg2 plus SO4 2 minus. Here it is Ca2 plus Cl minus. So this is a combination of 1 1, 2 2, 2 1. Now why I am writing all this? What is the purpose of writing different strong electrolytes? Is the reason that the value of A, that is the A value, will be same for the same type of electrolyte. Example, if I am going to take a combination of electrolytes where it is all 1 1 1 1 1 combination, right? For that particular group of electrolytes, my A value will be the same. If I am going to take a set of electrolytes where the charge of ions is 2 2, charge of cation and anion is in a 2 2 combination, that time the value of A will be the same. Or the third, if I am going to take a value of 2 1 combination with a set of electrolytes, again the value of A will be the same. Example, assume that there is a weighing balance. In a weighing balance, you know, there are 2 pans and I am going to measure my electrolyte, right? Let's assume we are taking the 2 electrolytes where my cations are the same. So I know the weight of my cation, so I put in my right pan the cation and also my left pan. But what happens is that the anions are different. So when I put the anions, what happens? The difference in the weight of anion will be causing the difference in the molar conductivity. The difference in the weight of the anion will cause a difference in the value of molar conductivity. Or in other case, if I know my anion weight both are going to be the same, then the difference in the weight of cation will cause a difference in the value of molar conductivity. Now to be more clear, I will just give you an example. Kohlrausch's law was focusing on examples of so many electrolytes and he found out some regularities in those electrolytes. What was the regularities? He said, now clearly observe children, when he took KCl, NaCl, if you see KCl and NaCl, only the cations are different but the anions are the same. When you take KBr, NaBr, again bromine, both the anions are same but cations are different. Again a combination Ki, Nai, anions are same, cations are different. The value of A was the same, which is 23.4. It is a molar conductivity, right? Now what is concluded again, when I take a combination where my anions are the same, cations are different, or in other case when I take an example where my cations are the same but my anions are different, again the value is remaining the same. So this is called as Kohlrausch's law. So when he did so many experiments with different combinations of electrolytes where cations being the same, anion being different, or anions being the same and cations being different, the value was remaining the same because the combination of the electrolyte, the charges, was the same for the set of electrolytes. So this was given by Kohlrausch's law. So now we will be seeing what is Kohlrausch's law, and also we will be looking for how to calculate for the combination of cations and anions, and then we will get into weak electrolytes. So Kohlrausch's law can be defined as limiting molar conductivity of an electrolyte can be represented as sum of the individual contributions of anion and cation of the electrolyte. What does it mean? Now for your convenience, I have put limiting molar conductivity as E naught of M. So E naught of M will be equal to lambda naught Na plus, which is a cation contribution, and this is limiting molar conductivity of anion, which is Cl minus. So for NaCl, which is a strong electrolyte, the limiting molar conductivity will be the combination of the limiting molar conductivity of individual ions, individual cation plus individual anion, that is sum of the individual contributions. So, if I have NaCl, it will be Na plus plus Cl minus, which can be further written as V plus lambda naught plus V minus lambda naught minus, which means this V plus and V minus will be the number of ions which are dissociated on dissociation. That is, once I put my electrolyte into the solution, the ions that are getting dissociated, it will be 2, 1 or it can be 3. So, that depends on the number of ions on dissociation. And what is lambda naught plus and lambda naught minus? Those are the limiting molar conductivity of the ions which will be given to you in the question. So, knowing all these values, you will substitute in the problems to get the value of the limiting molar conductivity of the excuse me children, limiting molar conductivity of the electrolyte. Now, that is when we have a strong electrolytes. When we studied that strong electrolytes and weak electrolytes, they behave differently. That is nothing but the extent of dissociation. Like whenever we take strong electrolytes like sodium chloride, when we take weak electrolytes, we will take acetic acid. Now, acetic acid at higher concentration, they have a poor dissociation power, that is they dissociate very poorly at a lower extent at a higher concentration. That change, there will be a change in the molar conductivity on dilution. We know when there is a dilution, the volume increases. So, what happens? The molar conductivity will increase. Why there is an increase? That is due to the increase in the degree of dissociation and the number of ions which are contributing to the total volume of 1 mole of electrolyte. Whenever before we were discussing the Kohlraasch law, I told you whenever we take area, that is volume, it is 1 mole of an electrolyte. So, when it is diluted, we should know about the number of ions per unit volume, that is the number of ions in the total volume of 1 mole of electrolytes. When that increases, that is contributing to the change in the molar conductivity. But that is in case of normal dilution, you can calculate the molar conductivity. But what happens in the situation where there is an increase in the complete dilution, that is when there is more water added to it, that is solvent added to it, when the concentration becomes so low that the electrolyte dissociates completely. There will be complete dissociation of electrolyte at that point of time, which we call it as alpha is equal to 1. +1 signs, we have studied this. If you remember, alpha is the degree of dissociation, right? So, when C is equal to 0, my alpha will be equal to 1. So, that is a situation where the concentration reaches a value of 0. The alpha, that is the degree of dissociation, will be equal to 1. But what is alpha? What is my degree of dissociation? That is equal to lambda m, that is molar conductivity divided by limiting molar conductivity. So, my lambda degree of dissociation will be equal to molar conductivity divided by limiting molar conductivity. Now, this value I am going to substitute in my equation, which we will be doing it right now. We know alpha is equal to molar conductivity by limiting molar conductivity. But in +1, if you remember children, we have studied the dissociation constant for acid. Ka value is equal to C into alpha square by 1 minus alpha, right. So, what is alpha now? Alpha is lambda m by lambda naught m. So, this I will substitute in the equation where in the place of alpha. So, it will be C into lambda m, lambda naught m the whole square by 1 minus lambda m by lambda naught m. Understood? Now, what will happen? This is in denominator, so this will come down. So, C into lambda square m lambda naught m square into, now this is 1 minus, so this I can take, right. So, this will be lambda naught m by lambda naught m. That is, when this comes like this, you know, you can cross multiply and get it. So, still again this is in denominator, this I will take it to the numerator. So, C into lambda square m into lambda naught m by lambda naught m the whole square into lambda naught m minus lambda m. Now this value is the same, so I can cross it. So 1 will be reduced. So the final value for dissociation constant for a weaker acid is C into lambda square m by lambda naught m into lambda naught m minus lambda m. So this is nothing but dissociation constant for an acid. Why we are discussing all this is because of Kohlraasch law. So Kohlraasch law applications, if you see, it is helpful in calculating the molar conductivity of the electrolyte by getting, that is by adding the values of the individual contribution of cations and anions. Also it is useful in calculating the dissociation constant for weaker acids like acetic acids once we know the degree of dissociation. Here in place of degree of dissociation alpha, you put the value of lambda m and lambda naught m. And as we know, once you calculate these two, you can easily substitute for the value of alpha. So I hope children you have understood till this now. So children, we have studied till Kohlraasch law, and this is the last part of the chapter, which is electrolytic cell and electrolysis. Electrolytic cell, this we have been learning right from our 10th standard, right? We have studied about that is galvanic cell or Daniell cell, and also about electrolytic cell. Electrolytic cell is a cell where electricity is used to produce chemical reaction, unlike our galvanic cell. So what happens here? We are going to take two electrodes, that is an anode and a cathode, both made up of copper. So one is an impure copper, the other one is a pure copper. And here copper undergoes both oxidation and reduction, because in normal galvanic cell we have learnt a higher reactivity metal, that is we know there is a reactivity series, and the more reactivity metal will displace the less reactivity metal. That is, the more reactivity will undergo oxidation and the least reactive will undergo reduction. But here in this case of electrolytic cell, copper loses 2 electrons to become copper 2 plus at anode, that is oxidation occurring at anode, and at cathode copper 2 plus will take up those 2 electrons to give copper, that is getting reduced. What is exactly the situation is? It is an electrochemical cell. When we pass electricity, that electricity produced is going to help us to produce a chemical reaction. That is how chemical energy is generated. So that is with respect to electrochemical cell, or you can say electrolytic cell.
Electrolytic cell. An electrolytic cell has the ability to decompose chemical compounds by converting electrical energy into chemical energy through a process known as electrolysis. The basic structure consists of an electrolyte and 2 electrodes, the cathode and the anode. The electrolyte is usually a solution composed of water and dissolved ions or molten salts such as sodium chloride. An external voltage is applied to the electrodes. The electrolyte will release ions that flow to and from the electrodes. At the electrodes, charge transferring reactions known as redox reactions will take place. Because the redox reaction in an electrolytic cell is non-spontaneous, electrical energy is required to drive the reaction. Electrolytic cells are used in the preparation of pure substances such as aluminium, magnesium, sodium, calcium, and high-purity copper. Let's examine an example using molten sodium chloride as the electrolyte. When a current is passed, molten NaCl is electrolyzed. 2 distinct reactions will occur at the cathode and anode. Here are the reactions at the cathode, our negative electrode. First, the positively charged sodium ions in the electrolyte will migrate towards the cathode, where they will be reduced to sodium metal. And here are the reactions at the anode, our positive electrode. Chloride ions will migrate towards the anode. Electrons will be pulled from the chloride ions and, as a result, the chloride ions will be oxidized, forming chlorine gas. Summary. An electrolytic cell is a device in which electrical energy is converted to chemical energy. Positive ions in the electrolyte migrate to the negative electrode known as the cathode. Negative ions migrate to the positive electrode known as the anode. Electrolytic cells are used in the production of pure substances.
Was studied by a scientist, Michael Faraday. He was going on doing several experiments with different electrolytes and different electrodes, and then came to a conclusion with his two Faraday's law. What are those? The first law states that amount of chemical reaction which occurs at any electrode, it can be my cathode, it can be anode, whichever electrode it can be, that is oxidation electrode or reduction electrode, the amount of chemical reaction, what do you mean by amount? That is the quantity. It is depending on, or it is directly proportional to the quantity of electricity passed in the solution or passed through the electrolyte. I am taking an electrolyte, let us assume copper sulfate or copper chloride, and when I am going to pass my electricity, now whatever is the amount of electricity I am passing, that is giving out the amount of chemical reaction which has to occur at the respective electrodes. Or in other words, I will say the chemical reaction that is occurring at the respective electrodes, it can be anode or cathode, depends, or it is directly proportional to the quantity of electricity that is passed through the electrolyte. You understood, children? This is what is the Faraday's first law of electrolysis. What is the second law states? The second law states that the amount of different substances liberated by the same quantity of electricity passed through the solution is directly proportional to their chemical equivalent weights. I repeat, listen. Amounts of different substance liberated. Some substances get liberated, get evolved out by the same quantity of electricity passed. Whatever is the amount of electricity passed through the electrolytic solution is proportional to their chemical equivalent weight. What is chemical equivalent weight? It is the atomic mass into the number of electrons which is getting reduced. Okay, that is the second law of Faraday. Before and all, like Coulomb meter was used to find out the quantity of the electricity. That is, it was a big device which was used, but nowadays it is isolated, we don't use those things. But we have different devices for calculating the electricity. So what do we do is to find out Q, the value of the charge of ions Q, we put it is I into T, where Q will be measured in coulombs, I, the current, will be measured in amperes, and the time taken for passing that electricity through the solution will be measured in seconds. So this is the formula which is important. Now I'll be just giving you two examples to understand Faraday's law in an easy way.
Faraday's first law of electrolysis. Michael Faraday, a British physicist, experimented on the passage of electricity through liquids in 1834. From those experiments, Faraday derived two laws of electrolysis. Faraday's first law of electrolysis states that the mass of a substance deposited or liberated on an electrode during electrolysis is proportional to the total quantity of electric charge passed through the electrolyte. This law can be illustrated in the process of electroplating. In electroplating, the metal to be plated, silver as an example, is used as an anode. The object to be plated, an iron spoon as an example, is used as a cathode. A silver nitrate solution is used as an electrolyte. When the current flows through the electrolyte, silver ions move to the negative electrode and deposit them there. Consequently, the silver rod continuously dissolves into the solution and gets deposited on the iron spoon. The rate of deposition of the metal onto the object increases with increase of the electricity. The law can be expressed in the equation M is directly proportional to Q, where M is the mass of the substance liberated at an electrode, and Q is the total electric charge passed through the substance. Summary. Faraday's first law of electrolysis states that the amount of substance deposited on an electrode by electrolysis is proportional to the current flow through the electrolyte.
As we have discussed about Faraday's law, that is the two laws which is relating to the Q, that is value of Q will be is equal to 1 into T. Now how to calculate the Faraday's constant? Because we were using Faraday's constant, if you remember, in our Nernst equation and other equations where F, in place of F we used to put some value. Now how did it come? Now we will see any metal, if it is getting reduced, you know it has to accept electrons. Gaining of electrons, it undergoes reduction. So here Ag plus on aqueous state will take up one electron to become Ag, that is solid. So here 1 mole of electron is required for reduction of Ag plus. That is 1 electron is required, 1 mole of electron for Ag plus to accept that and become silver solid. But we know the charge of 1 electron is 1.6021 into 10 power minus 19. This we have learnt in +1 science, right? Now, charge of 1 mole of electron will be what? Because we know 1 mole of any atom will be is equal to Avogadro number, which is 6.022 into 10 raised to 23. So, when charge of 1 electron is this much, charge of 1 mole of electron will be Avogadro number into 1.6021, which will be equal to 96487 coulomb per mole. This value C will be calling as a Faraday's constant. So, this we will be mentioning at F. So, here 1F is equal to 96500 coulomb per mole. So, for Mg2 plus in ionic state, if it has to accept 2 electrons to get reduced to Mg solid, or aluminium 3 plus taking up 3 electrons to become aluminium solid, what will be the value of F here? It will be 2F because 2 electrons are taking part in the reduction and here 3 electrons are taking part in the reduction. So, it will be 2 into 96500 and for aluminium it will be 3 into 96500. So, this is the way which is giving rise to the value of the Faraday's constant. So, this is what you will be using. This can come in 1 mark question. They can give you the equation and they can ask you to calculate the value of 1F or 2F. So, depending on the number of electrons that is taking part in the reduction process, you will be mentioning this. Is that clear, children? Hope you understood. Now, you will be seeing a small video which is explaining about the product of electrolysis. So, when you understand that, I think it will be easy for you to follow up, because this we have already studied in our 10th standard, where the molten state, the nature of electrolyte and also the different ionic forms of the electrolyte. So, that will help you to understand much better what are the products that can be formed during the electrolysis. So, children, with that video we will be stopping our class for today, and later in the next class, that is on Saturday, I will be posting a video on batteries, that is primary and secondary batteries, and also about fuels. So, hope this class was fruitful for you. If you have any doubts, kindly call me, children. Thank you so much.
Products of electrolysis. During electrolysis, oxidation occurs at the anode and reduction occurs at the cathode. The products of electrolysis depend on the nature of electrolyte, the type of electrode used, oxidizing and reducing agents in the electrolytic cell, and the respective standard electrode potentials. Let us see how each of these factors affect the products of electrolysis. Nature of electrolyte. The electrolyte can be either in the molten or in the aqueous form. Type of electrode. The electrode used could be a reactive electrode like copper, which can take part in the electrolytic reaction, or an inert electrode like platinum, which does not take part in the electrolytic reactions. Let's take a look at how the products of electrolysis differ with different types of electrolytes and electrodes. The products formed under different conditions with respect to the nature of electrolyte and type of electrode used differ during the process of electrolysis. Click each tab to learn more. The electrolytic cell consists of platinum electrodes and molten NaCl as the electrolyte. Molten sodium chloride contains sodium and chloride ions. During electrolysis, the positively charged sodium ions move towards the cathode, where they take up electrons and are reduced to form sodium metal, while the negatively charged chloride ions move towards the anode, where they lose electrons and get oxidized to liberate chlorine gas. The overall reaction that takes place during the electrolysis of molten sodium chloride is molten sodium chloride is electrolyzed to form sodium metal and chlorine gas. Electrolysis of aqueous NaCl. The electrolytic cell consists of platinum electrodes and aqueous NaCl as the electrolyte. Aqueous sodium chloride ionizes to form sodium and chloride ions in water, and water itself is slightly dissociated into hydrogen and hydroxide ions. There are two reactions that are possible at the anode. Chloride ions undergoing oxidation to liberate chlorine gas, and water molecules undergoing oxidation to liberate oxygen gas and hydrogen ions. The standard electrode potential of chlorine is higher than that of water, but the oxidation of water in a concentrated electrolytic solution is a slow process. So, during electrolysis, the chloride ion moves towards the anode, gets oxidized, and chlorine gas is liberated. Similarly, there are two possible reactions that can occur at the cathode. Sodium ions undergo reduction to form sodium metal, and hydrogen ions undergo reduction to form hydrogen gas. Now, since the standard electrode potential of hydrogen is higher than that of sodium, at the cathode, hydrogen ions undergo reduction to form hydrogen gas. Thus, the overall reaction that takes place during the electrolysis of aqueous sodium chloride is the liberation of hydrogen gas at the cathode and chlorine gas at the anode. Electrolysis of aqueous copper sulfate using copper electrodes. The electrolytic cell consists of a copper anode, a copper cathode, and aqueous copper sulfate as the electrolyte. Copper sulfate ionizes to copper and sulfate ions in water, and water itself dissociates into hydrogen and hydroxide ions. During electrolysis, the reactive copper anode undergoes oxidation. Each copper atom loses 2 electrons to form copper ions that are released into the solution. This results in the decrease in the width of the anode. These positively charged copper ions migrate to the cathode and undergo reduction. Each ion gains 2 electrons to become a copper atom. These copper atoms are deposited on the cathode. With this reaction, there is an increase in the width of the cathode. The copper ions undergo reduction as the standard electrode potential of copper is higher than that of positively charged hydrogen ions in solution. Did you know? Only pure copper obtained through electrolysis is used in the making of electrical equipment, since the presence of even small quantities of impurities in copper can reduce its electrical conductivity. The products of electrolysis depend on the nature of electrolyte, the type of electrode used, oxidizing and reducing agents in the electrolytic cell, and the respective standard electrode potentials.